Thin-walled products make up a significant portion of our product processing, particularly in the 3C, computer, communication, and consumer electronics, military, and medical industries. Let's take this product as an example. It has a thickness of only 0.5 millimeters, and we aim to complete it in one go without any additional support. Today, we'll delve deeply into the process. First, let's look at the product. The material is 6061 aluminum with a length of 300 millimeters and a wall thickness of 0.5 millimeters. Now let's discuss the machining method. Because the thickness of the material is smaller than needed during the blanking process, we plan to use AB glue for clamping. We can use a large fly cutter to mill the top surface and then finish the outer profile with a finish cutter. The process is relatively simple. Let's directly look at the final effect. After machining, we can remove it and finish the backing face in the same way. For the final face, we'll use a vise with 2 pieces of stock as spacers. We'll check the plane to see the difference. It's off by 0.26 millimeters, so we won't adjust it. We'll use an 8 millimeter cutter to mill out the middle groove. Since the structure is simple, we can directly look at the last step. Clamp the part using the vise, ensuring the straight edge is tight to maintain the 0.5 millimeter thickness. When the machining is done, use a dial indicator to measure it. If the dimensions are off, you can make a final pass. Now let's examine if the product is deformed. Before doing that, we need to analyze the key factors contributing to product deformation. 1, the larger the product size, the more prone it is to deformation. 2, softer materials are more likely to deform, such as non-metallic materials like nylon. 3, weaker structural materials are more prone to deformation. These 3 factors are given by the customer and cannot be changed. However, we can control 2 aspects. 1, aggressive machining parameters increase the likelihood of deformation. 2, using a clamping fixture that minimizes external force reduces deformation. Returning to this product, it meets several conditions for deformation. 1, size, with a length of 340 millimeters, height of 32.5 millimeters, and width of 22.5 millimeters, it's prone to deformation. 2, material. It's made from common 6061 aluminum, widely used in the 6 series aluminum alloys. 3, cutting parameters using an 8 millimeter cutter, a depth of cut of 0.5 millimeter, spindle speed of 5,000 RPM, and feed rate of 3,000 millimeter per min. I manually control the cutting amount to minimize deformation. Regarding clamping, we didn't use AB glue as it's not very effective. Instead, we used a vise with a torque wrench set to 25 millimeters, ensuring a consistent clamping force. The torque wrench used previously remains set at 25 millimeters. 2 critical areas to consider. 1, the 0.5 millimeter thickness. 2, the overall groove not expanding or contracting. To address the 0.5 millimeter thickness, we need precise machining parameters, taking a 0.5 millimeters cut, leaving 0.1 millimeters, and using the vice's sidewall as support without excessive force. For the groove, avoid excessive force during clamping to prevent inward deformation. Post-machining, if excessive force was used, the part would deform inward once unclamped. Finally, measure the outer shape to check for any deviation. Understanding the fundamental principles of product deformation allows us to control the process effectively. It's quite straightforward. That's all for today. If you enjoyed this content, please like, follow, and support us. I'll share more factory tips and knowledge for your learning and reference. See you next time.